Hello viewers, welcome back to our channel. It's still Shaka Annual, the math tutor. Welcome back to the Math in Motion. Today, as we promised that we shall be talking about the Markov chains as a part of the stochastic modeling. Today, Markov chains, here we shall consider specifically a process where the future depends on the past, where the future depends on the present but not the past. Here, examples of Markov chains, we may have a simple random walk. Remember, for a simple random walk, we shall always be moving forward. In order for us to move forward, we shall always depend on where we are. Examples of, a basic example of a Markov chain. If we talk about, let's talk about days. In order for me to record the number of people who come in to, if I'm trying to measure or to count the number of people who are coming to a certain building to buy something, I'll always note that the number of people who will be there tomorrow will depend on the number of people who are there today, not in the past. But today now, we are going to divide our Markov chains into two types, where we have the discrete Markov chains and continuous Markov chains. But today, we shall see how to deal with the discrete Markov chains. Here, under discrete Markov chains, here we say the state changes from a certain discrete time instance indexed by the integer n, and at each time step n, the state of the chain is noted by xn and belongs to the finite number of possible a finite set of possible state spaces. We assume our s to be 1, 2 up to m, where m is a positive integer. We are saying that here we're going to look at a variable. This variable under a Markov chain, this variable, we're going to divide our time into different time slots, but these time slots have to be of discrete time instance. As in, remember, we know that time is always continuous, because if they ask you what's the time now, count that right now it's just exactly this time, because at the time we are going to be talking, some seconds will have moved. But now here we want to divide our time into time slots. We want to assume that time now is in discrete times, as in, if we talk about seconds, let us talk about seconds in discrete times. Like we talk about 1 second, 2 seconds, 3 seconds, up to m seconds we want. If we're talking about days, we're talking about now 1 day, 2 days, 3 days, 4 days, because our m has to be a positive integer. And this time around, we're going to see the probability for us to transfer from one state to another, as in the Markov chains is described in terms of transition probabilities, Pij. Whenever the state happens to be in I, there is a probability Pij that the next state is going to be j. I'm saying that here I want to describe our Markov chains in terms of probabilities. And these probabilities will always depend that for me if I'm in state I, if today is Monday, therefore tomorrow is going to be Tuesday. And then mathematically we can say that for me, probability of xn plus 1 being j, given xn equal to I, equals to Pij, and then this is our transition probability. But remember that if I try just to make it into a layman's language, probability of xn plus 1 means the probability of the future. If the future is j, given the present being I, gives us the Markov chain, which is the Pij, because we said that Markov chain is always, we shall always determine the future depending on the present but not the past. Therefore, mathematically, shall always present our Markov chain as a transition probability Pij equal to the probability of the future, probability of tomorrow being j, given the present, given today is I, is the same as having probability of Pij, where I and j are all contained in our state space S. I'm saying that if we're talking about time, into the probability of tomorrow being j, given today being I, is the same as having Pij. We are transiting from I to j, transiting from today to tomorrow. Now, the key assumptions underlying the Markov chains is that the transition probability is Pij applies whenever the state I is visited, no matter what happened in the past and no matter how state I is reached. This is the key assumption we're going to take under the Markov chains, that the transition probability is Pij applies whenever a state I is visited, no matter what happened in the past. Here we won't be able to know what happened in the past, shall always depend on what is happening in the current to predict the future, and no matter how we have arrived to this state I. shall not be concerned with how we arrive to this state I and what happens in the past before the state I. Now, mathematically, we shall always assume a Markov property which requires that the probability of the future depends on the past irrespective of the the probability of the future depends on the current irrespective of the past. Here I am saying that probability of xn plus 1 equaling to j given xn equaling to I. If you just take in this into layman language, you shall say that xn plus 1, this is the future. I'm talking about tomorrow, the future, given xn, just the past, just today, because this is xn. But then xn minus 1 is going to be yesterday but 1, then up to the first day x naught. Now for a Markov chain, we say that we shall always ignore the past and just go with the present and the future. Then for all of this chain, we just extract this only part, this part only. The probability of xn plus 1 equaling to j given xn equaling to 1, and it's the same as having probability Pij, which is our transition probability as we saw. But now, for transition probabilities, Pij must be positive, and the sum of the rows have to add up to 1, meaning that summation from j equaling to 1 up to m, Pij equaling to 1 for all I. I think for more understanding, we shall need to do some examples for you to get to know what we are dealing about with Markov chains. But what we have to take into this first part is that a Markov chain, we are dealing with the future. This is the process where the future depends on the present but not the past. That's the first thing. We have to assume our state space. State space may be 1, 2 up to m. State spaces may be, okay, if you just give an example, a simple example of today raining and not raining today. Today we may have a state of raining or not raining, and tomorrow we may have a state of raining, not raining. Now, for us to determine what will happen tomorrow based on what happens today, it's called a Markov chain, because we want to know what will happen tomorrow. Will tomorrow rain given today it rains? Will tomorrow not rain given today it rains? Now that is a Markov chain, what you're going to be dealing with. And then our states will be raining and not raining. Therefore, our states will be 1 and 2. Therefore, raining and not raining are the states, and those states, we are saying that those states are our positive integers. But now, we shall always need to know that in order for us to get the transition probability Pij, we shall always need to know what will happen in the future given the present. Will tomorrow rain given today it has not rained? And then we have to know that for all these probabilities Pij have to be positives, and if you have a negative probability, then that cannot happen. And lastly, what we have to know that if we sum the all probabilities for a given row have to be equal to 1, as in a given row, when transiting from state 1 to state 2, state 1 to state 1 up to state n have to be giving me a 1. I think we can go ahead and see some examples on how we can do this. Now we shall always present our transition probability into a matrix, transition probability matrix, as this way. Probability Pij is, remember, we are transforming from one state to another. I'm transforming from, remember, we have S states. We have a set S of possible states, which have state 1, state 2 up to state m, where m is a positive integer. Therefore, we shall always present our transition probability in the form of a matrix, showing that for me transform here will be a probability of me transforming from state 1 back to state 1. This will be for me transforming from state 1 to state 2, for me transforming from state 1 up to state m, transforming from state 2 up to state 1, transforming from state 2 to state 2, and then as we see like this. As an example, we had our states. I gave you an example. We just talked about it. That example, we have our states to be it may rain or not rain. It may rain or not rain. We have in two states here. We have, if we say 1 to start for raining and 2 starting for not raining, we shall always say that we want to know the probability that tomorrow x2, it will rain. Given x1, it rained. Now, this is a Markov property because we shall always say that the future, x2, okay, what will happen in time period 2 will always depend on what happens in time period 1. And then here we're talking about that we are transforming from 1 to 2. Therefore, shall be able to read our value from the transition probability, which is probability of 1 to 2. We are transforming from state of raining to non-raining. State 1, then 2. This transition probability matrix is going to help us to get those values of the probabilities when one is transforming from one state to another. I think for this is going to be quite interesting. Let us see an example now. This example will enable us and appreciate more. Okay. Yeah. Yes, now we can do an example. I think this example will help us appreciate more. Our example 1 says that Alice is taking a probability class in each week. She can either be up to date or she may be fallen behind. Now, if she is up to date in a given week, the probability that she will be up to date or behind in the next week is 0.8 and 0.2 respectively. Now, if she is behind in a given week, the probability that she will be up to date or behind in the next week is 0.6 and 0.4 respectively. Now, we are sure that the probabilities do not depend on whether she is up to date or behind in the previous weeks. Therefore, let us state the transitional probability matrix and then the transitional graph. Now, from this statement here, that we are sure that the probabilities not depend on whether she was up to date or behind in the previous weeks, just gives us a view that we are talking about the Markov chains. Because Markov chains, the future depends on the current, not the past. And now here, what you have to know, the first thing, you have to first state you have to know your states. The first thing is you to determine your states. Now, from this question, the states are she's either going to be up to date or she's going to be falling behind. Now, it says we have state 1, which is, may select state 1 be, saying that state 1 is up to date. And then state 2 is saying that she may be falling behind. She may be falling behind. Just say behind like this, just. You have to first identify your states. Your state 1 is being up to date and state 2 is being behind. Now, the given probability is that if she is up to date in a given week, what is the probability that she will be up to date or behind in the next week is 0.8 and 0.2. This means that if the probability of me being up to date in the first week and being up to date in the second week, I'm transforming from being up to date in the first week to up to date in the following week is 0.8. And then probability of being up to date and then being behind the second week is going to be 0.2 from this statement. So that the probability that she will be up to date or behind in the next week is 0.8 and 0.2 respectively. The probability of me being, of she being up to date in the first week and being up to date in the next week is 0.8. And the probability of her being up to date in the first week and being behind in the second week is 0.2. I think we are together. And then now if she's behind in a given week, the probability that she will be up to date or behind in the next week is 0.9 and 0.4 respectively. Now, the probability of her being behind in the first week and being up to date in the next week is going to be 0.6. Then probability of her being behind in the previous week and being behind in the following week is 0.4 from this statement respectively here. We are saying that we are transforming from the future to the present. We are saying that probability of me being behind in this week and I be up to date in the next week is 0.6 and this one is this one. Now, if we have these transition probabilities, we can easily formulate our transition graph. But in the way that our Pij, so we can get our transitional probability matrix. So that our Pij is the same as having, now P11 is going to be 0.8. Then this is going to be P12 is going to be 0.2, and then 0.6, then 0.4. from here, we are seeing that our probabilities Pij are all positive, and sum of each row gives you a 1. 0.8 plus 0.2 is 1, and 0.6 plus 0.4 is a 1. That is our transitional probability matrix, Pij. From there, if you are able to have this Pij, then you can easily get your transitional graph. How you get the transitional graph? Remember, we have two states. We have state 1. This state 1 means it's being up to date. We have state 2 of being behind. But now we see that me moving from state 1 to state 1 is called safe transition, and I'm moving from 1 going back to 1. The probability is going to be 0.8. I'm moving from 1 to 1, 0.8. Now I'm moving from 1 to 2. In the period when I was up to date, and then period 2, I'm going to be behind. 1 to 2 is 0.2. Then I'm moving from 2 to 1. I was behind. I'm going to be up to date in the current period. It's going to be from 2 to 1 is 0.6. And then lastly, I was behind, and then I'm going to remain behind. It's going to be 0.4. I'm coming from behind, going back to behind, 0.4. And then with this is I've done to draw my transitional graph as this example here. I think as for now, I think you are started picking up what I'm trying to show you and illustrate. Let's do another example. In this example, I think I will comprehend more and appreciate more. Yes, now for example 2, I think also this example is going to help you appreciate what we are talking about. This example 2 is of a spider and a fly here. Now a spider moves in a straight line in a unit increment. At each period, it moves 1 unit to the left with a probability of 0.3 and 1 unit to the right with a probability of 0.3 and stays in the same place with a probability of 0.4. Independent of the past history of the movement, 2 spiders are lurking at the position 1 and 4. Now, if the fly lands on either 1 or 4, it is captured and the process terminates. Now, don't have to construct a transition probability matrix and a transition graph. Now, for this case, we are seeing that we have a scenario of a fly. A fly is moving on a straight line. It's either moving forward or backward. But when it moves forward, the probability is of 0.3. When it moves backward, is a probability of 0.3. Now, if it stays at that same point, the probability is 0.4. They're telling us that independent of the past history of the movements. Now, for this part, independent of the past history of the movements, shows us that we are talking about Markov chain. 2 spiders are lurking at position 1 and position 4. Now, if the spider lands there, either on position 1 or position 4, it is captured and it is eaten. Well, it is eaten, yes. Now, then the process will just end there. Therefore, to not be able to move back to any position it has been before. Now, let us construct a transitional probability matrix. Now, for this question to be simple, we have just sketch something like to make it a C. We have to first do on part 2 before we do part 1. We have 1 step, 2 steps, 3, and then a 4th step here. We are saying that a fly is moving along the straight line 1, 2, 3, and 4. But now, if this fly reaches 1 here, it's going to be captured. Well, here there is a spider, so it's going to eat it. And then also here there is a spider. If a fly reaches here, bagana kujidia. Therefore, if we try to say that a fly began from here, can either move forward or move backward from this step and this step here. Also here, it can either move backward, but they cannot move forward because at this step here, it is going to be eaten. Here there is a spider. A spider again. The spider is going to eat this fly when it reaches step 1. And then also here there is a spider. If this housefly it can come here, but it cannot come back here because at this step here there is a spider. A spider will eat it. Therefore, we want to see the probabilities that for a fly to go. If I begin from, he said that if I'm at 2, I can either move forward or move backward. If I'm at 2, if I move forward, I move forward with the probability of 0.3, as the question states that the probability of moving forward is 0.3, and the probability of moving backward is 0.3. From here to here is backward, I'm moving 0.3. So from here to here is 0.3. But remember now, there's no probability of me leaving 4. Therefore, if there's no probability of me leaving 4, therefore the probability of being at 4 here, staying at 4, is going to be 1. Because there's nothing like, I cannot leave this 4. If I'm at 4, I'm always at, if the spider reaches 4, it is at 4, because it's going to be eaten. I cannot come back to another step. Also, being at 1 here, the probability of being at 1 is 1, because if a spider reaches 1, here, it's going to be eaten. Therefore, this is going to be my transition graph, stating that if a spider begins this moving from step 2 here, from the second step here, it can either go to 3, and then it can also come back to 2 from 3. Then once it's at 3, it has 2 steps also. It can also go back, it can also go to 4. But for it going to 4, it cannot come back because it's going to be eaten at this step 4. This step 4 is called the absorbing state. It's going to be eaten. It cannot come back to this step 3. Also here at 2, can come back here, but for it going back to 2, it is impossible because at this step here is going to be eaten. Therefore, the probability of it being at 1 is 1, and the probability of being at 4 is 4. Then from there, we can also get our transition probability, Pij. The Pij now is going to be in this format. Remember, we have 1, 2, 3. There are 4 steps. 1, 2, 3, and 4. But these values, I'm just putting them there for just working. Therefore, they shouldn't be there on your answer. Now, for here, we are saying that we are moving from step 1 to state 1. P11 is going to be 1. Now, P12, since I cannot go to 2, there is a 0. Since I cannot move from 1 to 3 directly, as in move from 1 to 3 directly, also here is 0. Also, since I cannot move from 1 to 4 directly, here there is also a 0. And I said that the sum of a row is always equaling to 1. Yes. Now, for here now, I'm transiting from state 2 to state 1. I'm moving from 2 to 1. From 2 to 1, the probability is 0.3. From 2 to 1. Now here, from 2 to 2 itself, as we said that from 2 to 2 itself, we said that the probability of being at 2 and 2 itself is going to be 0.4. A house fly, this fly is going to remain in the same position with a probability of 0.4. And then also, the probability of 0.4 staying at 3 is 0.4. Now, the probability of me moving from 2, of remaining at 2, when I'm at 2 is going to be 0.4. Then the probability of me from 2 to 3, I'm moving from 2 to 3 is going to be 0.3. And then I think here is 0 because probability of 2 to 4, there's no one root that lead me to 4. There's no root that leads me to 4. Therefore, it's going to be a 0 here. If I add the row, I have to add up to 1. 0.3 plus 0.2 plus 0.3 is going to be a 1. And then now here I'm going to transit from 3 to 1. 3 to 1. There's no root that takes me to 1 directly. Therefore, I'm going to have a probability going to be 0. And another thing is going to be 3 to 2. And from 3 going back to 2, it's going to be 0.3. Then it's going to be another. It's going to be 0. It's going to be 3 to 4. Sorry, 3 to 3. Me staying at 3 is going to be probably going to be 0.4. And then the last one, 3 to 4 is going to be 0.3 because I can move from 3 to 4, 0.3. If I add the whole row, I have to add up to 1. 0.3 plus 0.4 plus 0.3 is 1. Now, for state 4, for moving from state 4 to 1 is impossible. I cannot move from here to here. Is 0. Now, for me moving from state 4 to state 2, from here to here, it's also impossible. It is 0. Then for me moving from here to 3, also it is impossible. It's going to be 0. Then for me from moving from 4 to 4, it's going to be a 1. Okay, the sum of the whole row has to add up to 1, as we saw that this is 0 plus 0 plus 0 plus 1 is 1. Therefore, my Pij is simply this one. This is my probability, transition probability matrix, Pij, for this question. I think we are picking something. Then let us do the last question about